Thank you very much. So this talk responds to work done by me and Miguel Areias, and it's a work that's been going on for a very long time. It's not as ambitious as it looks like from the first slide, so we're not actually going to rule the world, but we're trying to build a bridge to connect to different things, which is what the ring was supposed to do. So interfacing different languages is something that has been done for a very long time, since almost the beginning of having two different languages. Essentially, it's the ability to use two languages as if they are one. And it's very important in practice. It's important for Prolog, but this has also been the source of the success for Python in many ways. So do it naturally would be really great. And in this case, the goals that we have in our interface, which are the same as everyone else's, we'd like it to be transparent, meaning that you should be able to just use the system with the interface as it wasn't there. It should be efficient. It should slow down your system considerably. It should be generic, since it should work for any kind of program. And it should be elegant, because elegance is nice. So let's go to each point in time. So people have been doing this kind of interface in logic programming for a very long time, not as long as it seems from the slide, but for a long time indeed. So from almost the beginning of the area. Quintus Prolog has the first really nice interface that was developed for Prolog. It was also kind of similar to the Success Prolog one. And SWI has a lot of work on this area too, because SWI has been used by different communities. Like the first DRC interface, the GPL, which did the Java binding to Prolog, and Real, which we also collaborated in connecting Prolog to R, and then nowadays Janus for Python. So all these interests have been developed, and they do the same problem as what we are doing. Here, I wanted to talk about the differences in our interface though. So this is our beautiful design. And the main thing that we did, which is kind of interesting, is that instead of connecting directly Prolog to Python, we used C++ as a middle step. So the reason why we did that is because Python, now this is much more of an object-oriented language. And also because it makes the interface kind of neater and cooler, simpler to understand. We use a system called Swig for glue that doesn't have anything to do with SWI Prolog. It's an interface generator. It's I can say weapon with two. Well, it can be helpful and it can be dangerous. And we do the translation from our native C code to C code. Finally, we also added some libraries for language-specific functionality for Python stuff. I'll explain that later. So the foundations in the app are the C interfaces, or that were originally. The app underscore are the internal available functions. We call it app underscore because I'll call it app underscore. They're shared globally within the app, but they're not supposed to be exported. And they follow this methodology, which is essentially each data structure as a representation, an abstraction, a function to be constructed, they say, and an identifier. Okay? So we export that in a more kind of organized way, as in the C interface, the external C interface called EAP, with all the capital letters. It was designed just to isolate from the engine. It tries to export engine, fix some problems that have appeared in the work. And the app also supports this PL interface, which is actually the native 6 SWI interface. And it's a totally different perspective. Whereas we build terms and access terms, SWI is more about unifying terms, getting terms, and putting terms. So it's more like actually Prolog implementation in a sense. So all these things exist within the app. And the way we did the system is something like this. We start from we had these three interfaces built, C, C++, and SWI. We connect C++ to Swig. We connect SWI to a specialized term constructor that does the conversion from term Prolog to Python. And then that's it. So there's lots of interfaces going on here, which makes the system a little bit slower. But they're doing different things. C++ is constructing the objects. C++ and Swig are talking about objects and how you're going to connect to them. SWI and the lower interfaces are talking about how we can move from Python to Prolog and back. I'll try to explain that later. So the original object-oriented interface, the one I should explain better here, is essentially has four classes, four types of classes. The first one is called the app term, which is, guess what, manages terms. And the second one is called app engine, which manages the engine, the Prolog engine. The app A manages the atom table, which are the long-lived objects in Prolog. And finally, the app error, which takes care of errors. So the structure is like this. You have the C++ interface. You have these three types of classes. And for example, terms have several classes for every possible type of term. Applications, which are compound terms, pairs, integers, lists. You can construct lists, etc. So all these things will become available directly from Prolog to Python through the C++ interface. So each one of these objects will become a Python class. The same to the database. An atom will become Python property, will become an atom class, functors, etc. So all these things will become what you are going to use from Python. And if you just use it in the C++ interface, you can also do that. Actually, something of a little bit surprise for me was that I did the C++ stuff hoping it makes it easier to convert to Python, but actually it's of interest on itself. For example, this is a small program that's part of an XML reader. So the idea is that you just grab an XML package reader, which are plenty of them. Most of them are written in C++ or C. And then you just go to the C++ and adapt it to the interface to construct a term, a Prolog term. So that made it possible to construct a XML interface to Prolog in 1 week or so. So the key here is whenever you get a new attribute, you construct an application term, a compound term, and then there is some kind of bureaucracy going on, which I will not mention here because it's going to slow down things. So that's the basic idea for C++ interface. Error handling, you do it through this error objects that I mentioned. So an app error is shown down below, shown up here. So if the stack is not enough, you construct an app error object, assign it this type, and send it away. The idea is that the system actually manages to fill up the error object, and then the error object itself is neutral, language neutral, meaning that whenever you send an error, it can be interpreted in Prolog, in C, in Python, whatever. So this is a nice thing about the interface, that you can just do the error whenever you prefer. So the way you do it is essentially by just having a simple dictionary where the keys are strings, always, and values are strings and numbers. We can have temporary values like terms, but they're not allowed between the languages. Value, you can also copy a term, but you have to convert it into a string first. That's a simple idea. So now we get to the term, to the object transformation. So Swig is the system that we use, is essentially capable of translating C++ calls or C to Python. Not everything in C++, which is almost impossible. C++ is a really complicated language, but quite a bit. It's a very ambitious goal, and what happens is that if you try to do whatever they allow you to do, you're going to spend all the rest of your life programming Swig. And I think that was a big problem with previous users of Swig in this kind of project for Prolog logic programming, because they try to use it a lot. What we try to do is to just use it for one simple task, which is to convert objects from one side to the other, and all the rest is done by the lower level. So in this case, the way we do it is essentially by using these type maps. A type map says that given a certain object of a certain type, you're going to convert it into another object of a certain type by calling something. And that is, in our case, is always a library, bottom library built in, which is doing most of the work. So basically, essentially, our Swig declaration file is just a set of declarations how the objects connect to each other. That's it. This is annoying, by the way. I don't know how to get rid of it. So, oops. Okay. is based on a previous work with R. Essentially, tree walker. For Python to Prolog, just basically construct. There's nothing much to do. There's one problem with variable liveness. You have to be careful about not keeping around variables when they're left out on the stack. But that's not the problem with the construction of itself. Prolog to Python is a bit more complicated, not in terms of constructing the terms themselves, but in terms of what to do when we evaluate. Are you going to evaluate at the end or at the beginning? So Janus has the same problem. What we do is, we have a two option. We can either decide to do evaluation or immediately, or you can delay and construct a term for reflection. So by default in Python, we evaluate, because it's a language which evaluates. Left-hand sides in Python are kind of interesting, because the left-hand side will be the Prolog. And it can be a variable, so just set it and unify. It can be an atom, and in this case in the app, you set it as a variable. Or it can be a compound term, and in this case, the app tries to actually fill in the slots that are in some compound term with the Python subterms, which can be interesting. So these are the type maps that we use for doing the conversion between Prolog and Python. So integers get to be integers, and they go sent back to integers. So Prolog to Python, and then Python to Prolog. Floats are floats, so they are floats again. So this is so far so good. True is true, which is true. False is false, which is false. None is none, which is none. So none doesn't have a special meaning in Prolog, but we adapted one. Now, atoms, we have two types of atoms. The ones which belong to regular names, which are accepted by Python. And these are converted from Python to a Python symbol, and then back to a Python atom. Atoms which are, in Prolog atoms which are not understandable as a Python symbol, are converted to strings in Python, but not back. It doesn't make sense. Strings are converted into strings which are converted into strings. Lists are converted into lists, which are, although they are totally different structures. A Prolog list is a recursive data structure. Python list is essentially an array. Tuples are converted into something called T. Dictionaries are converted into a set of items. Again, SWI, for example, has a real native support for dictionaries. We don't. The app doesn't support dictionaries. It's a special term. It's just another term. But it kind of works. Finally, compound terms are converted either as a function or as a Python named tuple. Named tuples are kind of something similar to terms, so we use it very sorry, I was speaking too loud, maybe. And then that's it. That's the basic idea. Let's go. One kind of interesting question that we faced, and I think Jason, the same happened to the SWI and XSP community, was what we should do to translate atoms and strings. In Prolog, an atom is a symbol, and everything is a symbol. So originally, in terms of logic, atoms were everything. There was no strings in Prolog originally. But in terms of a programming language, then you have a different problem, because in a programming language there are strings, which are different from symbols. So if you think of Prolog as a logical language, it doesn't make sense to have strings. If you think of Prolog as a language, it makes sense to have strings. Ultimately, I think that Prolog is a programming language, like it or not, so we have it as strings. And when I started to make that decision, it was a very painful one for me, because I like atoms. But in the end, as the progress goes on, I've come to rely more and more on strings. They're kind of useful, really, although they're difficult to implement. So that's the decision we've taken, which is different from Janus. Janus also had to make this a similar kind of choice, and they decided to keep atoms as strings, which I don't really agree in the end. Notation. So in Prolog, a call to Python is something like this: a.b. A is the module, b is the function. So it's exactly what you have in Python, except that Prolog interprets it as a list. But you don't really have to know that, hopefully. In Python, we use name structures. Like, for example, you can construct a term by using a as a variable, which is constructed, B as a variable with a B constructor, and then let's do a term called current predicate, which has A and V. So you can construct, using these named tuples, you can construct any Prolog term. Now this is an example. It looks a little bit complicated, but it's not as much as it seems. So this is a user interface usage. In this case, the idea is to actually exploit, to understand ILP, Inductive Logic Programming, that our colleague was speaking before. So the idea is that in ILP, a lot of the work relies on having what people call a saturated clause or bottom clause. The bottom clause, the example that you want to prove, is usually in the middle. And what the bottom clause gives you is the relationships that it has in the database. So you can see each node in this graph as a path, as a node that is connected somehow to the predicate that you want to learn. In this case, you wanted to learn if this drug is active, atom is active, sorry. And to do that, you have these connections. But what the bottom clause usually tells you is very hard to understand because it's about, say, 800 literals followed one by the other. So the goal here, what I did in this example, is to transform the bottom clause into a graph, which is easy to do. And then essentially just paint the graph according to the names of the predicates that are being used. So you can see that, for example, these red ones are atoms. These are comparisons, and these are bonds. So this is a chemical example. So the atom is a drug. The compound is a drug. The atom is a part of the compound, and the bonds connect the atoms. And you can see that actually the way the structure is connected, created by the red saturated clause, is a little kind of a circle, which sort of come out from this active example. So basically there are the atoms which are close to the example, and as you go further away, you get to the bonds, etc. And that means in practice that when you exploit ILP, when you generate clauses, you're going to generate lots of clauses with atoms because they're closer. And then you're going to generate eventually atoms with examples. And then this kind of complicated stuff that we put connected, extra predicates that we generated, are going to be hardly used because they're not going to be enough time. So this was the first step of this research project that I did. Continue doing that by actually trying to quantify this. See which nodes there are more or less easy to use. So the actual code that does this thingy is this. This is a Prolog program, which is actually more like a Python program than a Python Prolog program. To generate the graph, it has the edges and the nodes. So it first defines two lists for the edges, sources and targets, computes the edge weights, and then it activates this blocks, D3 blocks module from Python, which does the real work. Actually, the real work is done by the D3, which is a JavaScript toolkit. So now what it does is, to call D3, it needs to create a data frame, which is pandas. This is Prolog code, by the way, from the dictionary, which is created by us using this notation that I mentioned about sources, targets, and weights. Then it calls elastic graph algorithm on this data frame using this file path, which is where the answer was stored, and the fixed size, because it's going to be pretty large. And then at the end, it sets information about the three nodes and calls the algorithm the elastic graph to show the result. So that's actually just the code that we used. It's basically the Python code plus the Prolog code to construct things. It's actually too much similar to Python sometimes, I think. Because you forget, for example, in Prolog you cannot have atoms or constants with low uppercases. So I always get these extra variables in the middle. Because it's also actually something that you cannot do in Python that you can do in the interface, which is actually you can use these three blocks. It could be a variable, and I could actually bind it dynamically at runtime. So I could construct this objects as I go along. This is an example of a Prolog interpreter. It was written in Python. So the core of the interpreter is just this simple algorithm. You have an engine, which has the query. It seeks to extract the query from the engine. For every element in the query, if it has bindings, add it to the engine bindings, the bindings list, print the bindings, if then go on. So basically, it's like in Janus as well, you just have to do a loop to get all the solutions for the query. Just this for I and Q. And that's about it. So I I've been using this for a while. I used it for a big application in mining, actually health data. And then this ILP has been used mostly for visualization, which is something that you can do with Python much better than Prolog, I can tell you. And also to interface Prolog to machine learning toolkits, like, for example, all things from neural networks to classical learners. So all these things work pretty well. The trick, though, is that you don't want to use interface very often. You want to have it around, but you want to do a few operations which move a lot of data in a single go. If you put a lot of fragmentation, then your system will become unstable and slow. Okay, thank you very much for listening so far.
Can you say a little bit about, I don't know hardly nothing about Prolog. How does it handle numbers? And are they compatible with Python's numbers, big ints, rationals, floats, IEEE, et cetera, et cetera?
Prolog systems, most Prolog systems like YAP and SWI, do handle big numbers and rational numbers. I think SWI also handles big floats, and I don't. YAP doesn't. The interface right now, I don't think it's supporting big numbers, but not so much because of Prolog's fault. But when we did the interface first, Python didn't have this supported standard. Now that it is kind of standard in the language, I think, then it probably is quite easy to include it. So essentially, what we want to do is to convert numbers from one side to the other. We have a minimal representation, like, for example, if we have an array, we convert it to a list. But we avoid doing that until the very end, because we might lose information. If you have a NumPy array, it has more information than what is suggested in the numbers there. We always be careful of not having conversions between types, in the sense that if you have a float, you should keep on having a float. If you have an integer, you should have an integer. Never to do something like convert to text. We tried doing that in R, the R real interface. It's a big mistake. Anything that is a float, if you change it, print it out, and read it back, it will be different. And it will create all kinds of bugs for your users. So we don't ever convert in the numbers between the two systems. They just transported from one side to the other. Does that answer your question?
Cost, but you don't convert it? Isn't that a contradiction?
I just strip the tag, you convert it into the format. I have an integer. I have an integer of equal size equivalent size in both systems.
So if you have a float, you send it over to Python. Python sends the same number back. Okay.
This is based on libraries, so there is no piping or something like that. It's just shared memory.
Other questions?
Mm-hmm.
So, Anilu didn't mention this morning, but she recently presented an approach at the last ICLP, I think, an implementation that combines Prolog and Python to have an interface with an LLM. So perhaps the interface that you have developed could also be useful in this for this kind of applications, because this is quite popular now. You can use Prolog for reasoning and an LLM as an interface, as a human interface for natural language. So perhaps this is another area where your interface could be useful.
There's stuff already, so it's not the interface usually is not that difficult. You have to support. They have an interface to. It's called to Torch, PyTorch, which is a library where most LLMs are based upon. So, for me, from that point of view, an LLM is just another PyTorch object. So it's easy for me to construct an interface to that. Now, whether I want to do it or not, there are other interesting things that you can do besides LLMs. Even in machine learning, they have a nice work, which is also quite challenging for logic programmers on the graph networks. And there are also various which are being open now in terms of machine learning. These LLMs work, but also graph neural networks, causality, that was mentioned before. And I think that having a way of communicating quickly with this community is very helpful for Prolog, both for the app and XSB and SWI. And other Prologs, of course. So I think it's really important. That's why you should listen to my talk. Well, I have listened.
Other questions? So in the title you mentioned inductive logic programming. So is anything very special in interpreting ILP and Python as compared to some Prolog to Python?
It's more. I think it's more like you have to be. So examples and most of the ILP data is stored as either facts or lists usually, either dynamical lists or statically as facts. In Python, you usually use NumPy arrays or nowadays they call people tensors, which sometimes are built on top of the NumPy object. So it's nice to have an interface that can quickly copy arrays from one side to the other. And that's something that actually I have supported from the beginning. But it's not even necessary. Because if you do it, for example, if you copy once time, then you can run the algorithm. It will probably take more time than the copy, much more time. Usually the more data you have, as I said before, the slower the algorithm will be. And so the less the data will actually care.
Okay, so thanks.